Look up at the night sky. Really look. The stars stretch in every direction, twinkling with a kind of distant certainty. Some are billions of light years away, and yet, somehow, it feels like there is no end to them. It's easy, almost instinctive, to imagine that the universe itself might stretch on forever. That's the idea behind the infinite universe theory, that space doesn't stop, doesn't curve back on itself, doesn't have an edge, and continues endlessly in every direction. On the surface, it's a comforting idea. Infinity seems neat. If the universe is infinite, there is no boundary to worry about, no ultimate limit to what exists. Every possible arrangement of matter, every kind of galaxy, every version of every world could exist somewhere out there. Infinity gives the mind a kind of playground where everything imaginable fits. But infinity is a dangerous word in physics. It's seductive, yes, but it's also misleading. Mathematically, infinity is a well-defined concept. You can write equations with infinity and manipulate it, and it works beautifully on paper. But just because a number or a concept exists in math doesn't mean it exists in the physical universe. Nature rarely gives us infinities. We don't encounter infinitely large objects in daily life. We only encounter infinity when we stretch our imagination beyond the scale of reality. Let's try a simple analogy. Imagine walking through a forest. You can see trees in all directions, and your line of sight keeps extending. If the forest is dense enough, it might feel like it goes on forever. But in reality, the forest must have a boundary somewhere, or it might change into a different landscape beyond the hills or valleys you can't see. Our universe is a bit like that forest. The light we can see has only traveled so far, about 8 billion years since the Big Bang. That defines our observable universe, a sphere with a diameter of roughly 93 billion light years. Beyond that, there is literally no light reaching us, no information to guide our assumptions. We are blind to everything past that cosmic horizon. Physicists often assume that the universe beyond our observable sphere is more of the same, stretching out uniformly. This assumption is called the cosmological principle. It's a useful tool because it simplifies our equations and allows predictions about the universe on large scales. But it's important to realize that it's still an assumption, not a proven fact. Just because the universe looks uniform where we can see it doesn't guarantee that it continues that way forever. It could be finite, wrapping back on itself in a shape we can't yet visualize. Or it could even be more complex than anything our minds can easily imagine. Infinity is attractive because it feels complete. It feels like it answers the ultimate question, what lies beyond? But the universe doesn't owe us an answer that satisfies our intuition. The more we look, the more subtle clues suggest that infinity may be a concept we are projecting onto a universe that is vast, yes, but not necessarily endless. The idea of infinity might be a crutch for our ignorance, a placeholder for the mysteries that we have yet to measure or understand. What we do know about the universe comes from what we can observe. This is called the observable universe, the part of space from which light has had time to reach us since the beginning of the cosmos, roughly 8 billion years ago. When we measure it, we find a sphere about 93 billion light years across, filled with galaxies, stars, and cosmic gas. It's enormous, almost incomprehensible. And yet, as vast as this observable universe is, it is only a fraction of the whole. Everything beyond that sphere remains invisible. We literally have no way to see or measure it, and therefore we do not know what is out there. Think of it like standing on a mountaintop in thick fog. You can see the peaks and valleys that are close enough for your eyes to reach, but everything beyond the mist is hidden. You might imagine the landscape continues just like the part you can see, stretching on forever, and that's natural. But the fog could conceal cliffs, rivers, valleys, or even entirely different terrain. That is the challenge we face with the universe. The observable universe is our mountaintop view through the cosmic fog. Everything else is speculation, informed by physics and models, but ultimately unproven. Astronomers measure the observable universe using light, which travels at a finite speed. The farther away an object is, the longer its light takes to reach us. This is why when we look at distant galaxies, we are seeing them as they were billions of years ago, not as they are now. We are literally looking back in time. But no matter how sophisticated our telescopes become, there is a limit. Beyond a certain distance, light from the earliest galaxies has not yet had time to reach us. That defines the edge of what we can observe, the cosmic horizon. Beyond that, there is darkness, not because there is nothing there, but because the light hasn't reached our eyes yet. To imagine the universe beyond what we can see, scientists often assume the cosmological principle, that the universe is roughly the same in every direction, even far beyond our horizon. This principle simplifies calculations and lets us make predictions about the large-scale structure of the cosmos. But it is still just an assumption. It is based on what we can observe, and our instruments are limited. There is no direct evidence that the universe continues uniformly beyond our observable sphere. The patterns we see might continue, or they might not. The universe could curve back on itself in ways that we cannot yet measure, or it could have structures entirely unlike anything we see in our cosmic neighborhood. It is humbling to realize that despite all our technological advances, most of the universe remains unknown. Even the vast observable universe is only a small window into the bigger picture. What we see can give us clues, but we must be careful not to assume that infinity follows from what we observe. The temptation is strong because infinity feels like an easy solution, a tidy answer to the question of what lies beyond. But physics is not about convenience. It is about what can be measured, tested, and inferred from reality. And right now, the reality is that there is a boundary to our knowledge, and that boundary is our observable universe. Everything beyond it is a mystery, waiting to challenge our assumptions and expand our understanding. Now let's talk about what we don't know. Beyond the observable universe lies the great unknown, a region of space we can't see, measure, or interact with. Physicists often assume that it looks roughly the same as the part we can observe. This is called the cosmological principle, the idea that on large scales, the universe is uniform and isotropic, meaning it has no preferred directions or special locations. It's a convenient assumption, and it works well for modeling the cosmos. But it's important to remember that it is only an assumption. We have no direct evidence that the universe actually continues uniformly beyond what we can see. Imagine standing at the edge of a lake, looking out at the water. You see waves, reflections, maybe a few distant boats. You might assume the lake continues the same way forever. But beyond the horizon, there could be islands, cliffs, or the lake could narrow into a river. There is no way to know until you venture further. The observable universe is our horizon. Beyond it, nature could be dramatically different. There could be regions of space that are curved, folded, or connected in ways that defy our intuition. The universe might even loop back on itself, forming a shape that is finite but unbounded, much like the surface of a sphere in 3 dimensions. From our perspective inside it, it might appear endless, but mathematically, it could be perfectly finite. Another possibility is that the distribution of matter beyond our observable sphere is uneven in ways we cannot predict. Perhaps there are enormous voids, clusters of galaxies far larger than anything we've seen, or regions where the laws of physics behave differently due to conditions set at the earliest moments of the Big Bang. All of these scenarios are consistent with what we know about physics, but we have no observational evidence for any of them. In fact, the farther we try to extrapolate, the more uncertain our assumptions become. This is the core difficulty with infinity. We tend to project our observations outward, imagining patterns repeating endlessly, because our minds crave continuity and order. But the universe is under no obligation to conform to our expectations. Even more fundamentally, infinity itself is a concept we understand mathematically, but struggle to grasp physically. In math, you can talk about infinite sets, infinite lines, or infinite sequences, and the equations work. In reality, infinity is never directly observable. We cannot measure it, touch it, or interact with it. Every measurement we make is finite. Even the largest distances, the greatest energies, and the most massive galaxies are all limited. So when we imagine an infinite universe, we are blending what we can measure with what we can conceive, which may not correspond to physical reality at all. The human struggle with infinity is partly psychological. It is easier to imagine infinity than to confront the limits of knowledge, to accept that there may be regions of space we will never see, and structures we cannot detect. We naturally extend what we can observe, filling the unknown with a mirror of the known. But doing so risks mistaking a convenient mental model for reality itself. The universe may be finite, vast, and complex, far beyond our ability to visualize. Infinity might be a mathematical tool, a placeholder for ignorance, rather than a feature of the cosmos. Recognizing this forces us to confront the unknown not with certainty, but with curiosity and humility, and to accept that the universe may be stranger than our imaginations allow. Infinity is seductive, but it is also one of the trickiest ideas in physics. We see it in equations, in mathematical models, and in theoretical concepts, and it feels almost tangible because our brains can manipulate it on paper. But in reality, nature rarely, if ever, produces true infinities. That's why infinity is often a signal that something in our theory has broken down rather than a direct property of the universe. Take black holes, for example. According to Einstein's equations, matter collapsing under gravity can form a singularity, a point of infinite density. That sounds mind-boggling, like the universe itself has been compressed into a mathematical abstraction. But most physicists suspect that true infinities don't exist in nature. Instead, they indicate that our current theories are incomplete. We need a deeper understanding, likely involving quantum gravity, to describe what actually happens at those extremes. The same caution applies when we think about an infinite universe. Just because the equations that describe space allow for infinity doesn't mean the cosmos itself is infinite. A simple thought experiment can make this clearer. Imagine a hotel with an infinite number of rooms. A guest arrives, and the receptionist can always find them a room by shifting the occupants around. Another guest arrives, and again, the hotel can accommodate them. Mathematically, this works perfectly. It's called Hilbert's infinite hotel paradox. But in the real world, you cannot actually build a hotel with an infinite number of rooms. Infinity is a useful abstraction, but it doesn't correspond to any physical reality we can touch or measure. Applying the same reasoning to the universe might be equally misleading. An infinite cosmos may be mathematically convenient, but it is not necessarily physically real. Consider also the problem of repetition. In an infinite universe, every possible arrangement of matter must occur somewhere. That means there could be countless Earths just like ours, identical in every detail, and countless variations slightly different. Mathematically, this is a logical consequence of infinity. Physically, it becomes almost absurd, because there is no way to verify it. We have no evidence of these duplicates, and we cannot observe them even in principle. Infinity turns our imagination into a space of certainties that may not correspond to reality. Infinity is also difficult because it conflicts with observation. The universe we see, even the observable part, is filled with structures, galaxies, clusters, filaments, voids. It has patterns, and yet it does not repeat itself in any obvious, infinite way within the regions we can observe. If the universe were truly infinite and uniform, we might expect some repetition, or at least statistical regularities extending endlessly. But the farther we look, the more subtle and non-repetitive the structure becomes. That suggests that infinity might not be the right way to think about the universe. The human struggle with infinity is understandable. We naturally try to extend what we know, imagining patterns stretching endlessly. Infinity is convenient, comforting, and easy to conceptualize. But reality is rarely convenient. The universe does not have to satisfy our intuition. Infinity is a powerful idea in mathematics, but in physics it is more likely a warning sign, a reminder that our understanding has limits, and that the cosmos may be finite in ways we are only beginning to glimpse. Accepting this challenges us to think more deeply, to question our assumptions, and to explore a universe that might be finite, vast, and stranger than our most expansive imagination. Even though infinity is tempting, the universe gives us subtle hints that it might not be infinite. One of the most important clues comes from the shape of space itself. Cosmologists can measure the curvature of the universe by studying the angles of light coming from the cosmic microwave background, the faint afterglow of the Big Bang. If space were truly infinite and perfectly flat, these measurements would reveal perfect geometry with no bending or curvature. So far, observations suggest the universe is remarkably close to flat, but flat doesn't necessarily mean infinite. Just as the surface of the Earth looks flat when you stand on it, even though it curves over long distances, the universe might appear flat to us while actually being finite on cosmic scales. Our instruments can only measure curvature within our observable horizon, so the true global shape remains a mystery. The cosmic microwave background itself also contains subtle patterns that might hint at finiteness. Tiny fluctuations in temperature and density tell us about the distribution of matter shortly after the Big Bang. Some of these patterns suggest correlations on very large scales that are difficult to reconcile with a perfectly infinite, uniform cosmos. In other words, the universe may have a global structure that is finite, even if unimaginably large. It might loop back on itself or have a shape that our minds struggle to visualize. These patterns are small and subtle, but they remind us that infinity is an assumption, not a certainty. Observing the large-scale structure of galaxies provides another hint. Galaxies form a cosmic web of filaments, clusters, and voids. If the universe were truly infinite and perfectly uniform, we might expect these patterns to repeat endlessly, or at least statistically converge toward uniform repetition. But we don't see that. The universe appears organized but irregular, with structures that continue to surprise us as we map them further. This irregularity suggests that infinity, at least in the simple sense we imagine it, may not hold. The universe could be finite, with a shape or boundary so vast that we cannot yet detect it, but finite nonetheless. Even the expansion of the universe gives us clues. Space is stretching, and the rate of expansion varies with time. Galaxies beyond a certain distance are moving away from us faster than the speed of light due to this expansion. This limits what we can observe and interact with, creating a natural horizon beyond which information cannot reach us. The fact that there is an effective boundary to observation challenges the intuitive notion of an endless, fully accessible universe. Infinity might exist as a concept in equations, but the physical universe is constrained by what we can measure and by the laws of cosmic expansion. All of this adds up to a subtle but important point: the universe may be incredibly vast, far larger than our observable sphere, but it is not necessarily infinite. The evidence we have does not prove infinity. It only shows that the universe is big structured and potentially curved in ways that are difficult to imagine. Infinity is convenient, comforting, and mathematically elegant, but the physical universe does not need to satisfy those criteria. Recognizing this forces us to separate imagination from observation, math from reality, and speculation from evidence. Accepting that the universe could be finite, but still unimaginably large, opens the door to questions that are even more profound than the idea of an endless cosmos. Humans have always struggled with the idea of infinity. Our brains evolved to deal with finite things: rocks, trees, rivers, the number of animals we could hunt. We can count, measure, and observe, but infinity exists only in abstraction. It is not something we encounter in daily life. When we try to imagine an infinite universe, our minds instinctively fill in the gaps, extending the patterns we see outward, repeating endlessly, because that feels comforting. But the universe does not owe us comfort, and it does not have to conform to our intuition. Consider the way we think about numbers. Counting is easy up to a point: 10, 100, 1,000. But at some stage, we stop being able to visualize or hold the number in our minds. Infinity is like that, except without an upper bound. You can write an equation with infinity, and the math works perfectly, but when you try to picture it, your brain struggles. This is part of why infinity is so tempting. It feels like a solution to the unknowable. If the universe is infinite, there is no boundary, no edge, no unknown. Every possibility is somewhere out there. It promises completeness, a tidy answer to the most uncomfortable question of all: what lies beyond? Yet the physical universe is rarely tidy. Even the observable universe is filled with surprises. Galaxies are not evenly spaced, voids appear larger than expected, filaments twist and curve. Patterns exist, but they are not infinite repetitions. Nature does not necessarily obey the human craving for endless regularity. Infinity may be a useful mathematical tool, a placeholder in our equations. But when applied to the cosmos, it is far from guaranteed. The real universe is constrained by what can be observed, measured, and tested. Beyond that, our assumptions are just guesses, informed by imagination and guided by mathematical convenience rather than evidence. Psychologically, infinity is also overwhelming. It is easier to imagine the universe as endless than to accept that there may be limits we cannot see. Accepting finiteness requires confronting uncertainty. The idea that there are regions of space that will forever be beyond our reach, regions whose structure and contents we may never know. That uncertainty can be uncomfortable because humans prefer patterns, predictions, and closure. Infinity gives the illusion of solving that discomfort, creating a cosmos where everything is predictable in principle because it must repeat somewhere. But that illusion may be exactly what keeps us from understanding the universe as it truly is. Our struggle with infinity also shapes how we think about time, causality, and existence itself. We assume continuity, that space stretches forever, that matter and energy extend endlessly, because it aligns with our mathematical models. But physics reminds us to test assumptions, to measure what we can, and to be honest about the limits of knowledge. The universe may be finite, vast, and curved in ways we cannot visualize, but it is also real, measurable, and ultimately knowable only within certain bounds. Accepting the limits of our observation does not diminish the majesty of the cosmos. It deepens it, highlighting the boundary between what we know and what remains mysterious. Infinity is seductive, but the universe may be finite. Recognizing this frees us from the trap of projecting our imagination onto reality and allows us to focus on the profound mystery of the cosmos as it is, vast, structured, and full of questions that stretch our curiosity far beyond the limits of our minds. Understanding that humans struggle with infinity is not a weakness, it is a guidepost, reminding us that the universe is stranger and more subtle than our intuition can grasp. Let's use some thought experiments to get a sense of what a finite but enormous universe might look like. Thought experiments are not just play, they are a way to stretch our understanding beyond what we can measure, to explore ideas that the universe makes difficult to grasp. They allow us to take what we know and push it to extremes, testing the limits of our intuition. Imagine a cosmic sandbox vast beyond imagination. Into this sandbox, you start dropping stars one by one, scattering them across the sand. If the universe were truly infinite, you could keep dropping stars forever, and the sandbox would never be full. No matter how long you worked, there would always be more space to fill, more stars to drop, more patterns to create. But what we actually observe suggests something different. The distribution of galaxies, the structure of the cosmic web, and the curvature of space all hint that the sandbox is not infinite. It is extraordinarily large, but it may have boundaries or a shape that loops back on itself, making it finite yet unbounded, much like the surface of a sphere in 3 dimensions. From inside it, the universe might feel endless, but mathematically, it could be completely contained. Here's another thought experiment. Imagine shining a flashlight across the desert at night. You can see the sand and rocks illuminated directly in front of you. Beyond that, darkness stretches out. You might imagine that the desert continues endlessly, but the darkness hides whatever lies beyond. It could be hills, cliffs, or an abrupt edge. Our observable universe is like that illuminated patch, the part of the cosmos from which light has had time to reach us. Everything beyond that horizon is unknown. We can make guesses based on what we can see, but we cannot verify them. The universe may continue with similar patterns, or it may change in ways we cannot imagine. Infinity would require that those patterns stretch forever, but we have no evidence to support that. We can also consider light travel and repetition. In a finite universe, light traveling across vast distances might eventually loop back, allowing us to see multiple images of the same galaxy from different angles or epochs. We don't currently observe these cosmic echoes in the way infinity would suggest, at least within our observable universe. That absence hints that either the universe is finite, or that it is so large that these effects are beyond our observational horizon. Even if finite, it would still be unimaginably huge, far beyond human comprehension, stretching across billions of light years. These thought experiments show us that infinity is not necessary to explain what we see. A finite universe can produce the same observable effects, a vast cosmic web, galaxies scattered seemingly endlessly, and structures so large they feel infinite to us. Infinity is seductive because it seems simpler and more complete, but simplicity is not a guarantee of truth. Nature is often subtle, and the universe may be finite in size while remaining profoundly mysterious in structure and scale. By imagining the universe in these ways, we begin to reconcile the enormous size we observe with the possibility that space is bounded. The cosmos may be finite, but it is still a universe of extremes, distances, times, and structures so vast they challenge our minds. Thought experiments like the sandbox or the flashlight remind us that what we see is only part of reality and that the unknown beyond the horizon is not infinite by default. It is a mystery waiting to be explored, measured, and understood. So what does all of this mean for how we think about the universe? The infinite universe theory is elegant, simple, and tempting. It promises completeness, an endless expanse that contains every possibility. But elegance and simplicity do not guarantee truth. What we actually observe suggests something more subtle, more profound, and ultimately more mysterious. The universe may be finite, vast beyond comprehension, and structured in ways we are only beginning to glimpse. Accepting this possibility changes not just how we understand space, but how we understand our place in it. Consider the implications. If the universe is finite, then every galaxy, every star, and every particle exists within boundaries that we cannot yet measure, but may in principle be able to detect. Light traveling across these distances may loop back. Patterns might emerge that hint at the global shape, and the universe itself could have a structure more complex than anything we have imagined. Finite space does not mean limited wonder. On the contrary, a finite universe can still contain the unimaginable. It can stretch across billions of light years, contain trillions of galaxies, and hold mysteries that challenge our understanding of physics, time, and existence itself. The vastness does not shrink when it is finite. It simply shifts our perspective from endless repetition to intricate structure. Infinity also changes the way we think about knowledge. If the universe were infinite, we might feel like we could never know it all, and that every discovery would be just a tiny repetition of what exists elsewhere. But a finite universe, no matter how large, allows for boundaries in observation and therefore boundaries in knowledge. These boundaries are not limitations, they are opportunities. They focus our curiosity, sharpen our experiments, and make every measurement significant. Every new observation could reveal patterns, shapes, or laws that are unique to our cosmic neighborhood. Understanding finiteness is not a restriction, it is a framework for exploration. Philosophically, the idea that the universe might be finite invites humility. We are not observers of an endless, indifferent infinity. We are participants in a cosmos that has structure, shape, and perhaps even hidden connections that we have yet to discover. It reminds us that the universe is stranger than our imaginations, that what we see is only a portion of what exists, and that mystery is not a gap to be feared, but a horizon to be explored. Finiteness does not diminish the grandeur of the cosmos, it amplifies it. It teaches us to be patient with the unknown and to value what we can measure while remaining open to the possibilities that lie beyond our current reach. The ultimate insight is both scientific and philosophical infinity is not guaranteed, but the universe, whether finite or infinite, is still vast, complex, and astonishing. Our assumptions about endlessness are human constructs, conveniences that help us think about the unimaginable, but they are not necessarily truths of nature. Accepting that the universe may be finite deepens our understanding, sharpens our curiosity, and enriches our sense of wonder. We no longer look up at the stars and see an abstract, endless void. We see a cosmos that has shape, structure, and depth filled with mysteries to explore. Reality becomes not a concept to fill with imagination, but a horizon to approach with observation, measurement, and awe. In the end, whether infinite or finite, the universe challenges us to think bigger, measure more carefully, and embrace the unknown. Recognizing that infinity might be a projection of our minds rather than a feature of nature changes everything. It is a reminder that science is not about comfortable answers, but about honest questions, careful reasoning, and the courage to face the vast, subtle, and beautiful reality in which we live. The cosmos may have boundaries we cannot see, yet it stretches our understanding in ways that feel limitless. And that is perhaps the most profound infinity of all.